when we were doing limits, we saw that we could use algebra quite frequently to help us compute the limits we want to compute. Now, derivatives are just limits. The definition of the derivative is a limit. And the derivative also has algebraic results that we will use. So right here there are 22 derivative formulas that we will have to know for the remainder of this course. Now there are 16 of them listed. There are going to be 6 more listed in a moment. So I'm going to just go through some of them now. So right here, I'm not formally defining functions. I'm just saying here's a function, and then there's its derivative. So first, the constant function. The derivative of a constant function is 0. We're not going to prove that, but you can see if you just take a constant function, a horizontal line, the slope of the tangent lines is 0 at any point. You could also use the definition of the derivatives to conclude that. The derivative of any constant is 0. Next one is known as the power rule. In all of these functions, x is going to be our variable. X is the most convenient variable. So here we have x raised to some number. Now this number can be any number. X raised to some number, you want the derivative of x raised to some number? Well, you take that number out front, you leave x alone, and then you take the exponent and you subtract 1 from it. So for example, if you wanted to find the derivative of x to the second, well, you could use the definition, or you could use this. I would recommend using this if you are not told to use the definition. We've seen how to do it with the definition, but here, if you have the derivative, you need the derivative of, say, x to the 2, well, or let's say x to the 3, that's a nicer number for this example. If n equals 3, well, the derivative is 3x to the 3 minus 1. So 3x to the 2. And we'll see examples of all of these in a moment. That didn't erase right. Okay, that's better. Now the next one, when we were computing limits, one of the most convenient things that we could do is if we had a number out front and it was multiplied, well, we could pull the number out and then do the limit. Well, we can do the same with derivatives. Number times a function here, f and g are functions. C is a constant, that says constant. But if you have number times a function and you want the derivative, well, all you have to do is leave the number out front and then take the derivative. Here we're using the f prime notation. So these are all primes in this second column on this first board of derivative laws. So if you have derivative of constant times a function, leave the constant out front and then take the derivative. And the next one, well, when we did limits of sums or differences, we could just do the limit one at a time. We can do the same with derivatives. If you want the derivative of a function plus another function, well, you do the derivative of the one and then add the derivative of the other, or subtract. Now, the next two, known as what? Product and quotient rules, tell you how to take derivatives of products and quotients. And these are, in a sense, the first derivative results that you might not necessarily expect. When we did limits of products, you could do limit of the first and multiply by the limit of the second. With derivatives, you cannot do that. With derivatives, you need to follow this formula for a product. Derivative of a product f times g is f prime g plus fg prime. So you do the derivative of the first one, multiply by the second, add the derivative of add the first times the derivative of the second. So when you do the derivative of a product, you do derivative of one, multiply by the other, and then you do the derivative of the other and multiply by the first. And for quotients, we also can't just do the derivative of the top over the derivative of the bottom. We need to follow this quotient formula. Derivative of a quotient, f over g, where the denominator is defined, of course, or where the denominator is not 0, of course, I should say, is the bottom function times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So that right there, that 2 is a squared. It's not a second derivative. That's not the notation for the next derivative. So we have bottom function, derivative of top minus top, derivative of the bottom over bottom squared. And you have to know all of these formulas. These will all show up. They will almost definitely all be tested in some capacity. Next, derivative of an exponential function. E to the x with base e is itself. Derivative of e to the x is e to the x. Derivative of natural log of x is 1 over x. Derivative of a general exponential function, b to the x, b is a constant, x is a variable, b to the x is b to the x times the natural log of b. Derivative of a logarithm function with a different base, with a base other than e, is 1 over x times the natural log of that base. And then we have our trig functions. Derivatives of the trig functions. Well, derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Derivative of cosecant is negative cosecant cotangent. And all of these have x's in them, but I find them easier to talk about, easier to remember if you kind of ignore the x's. Derivative of secant is secant tangent. The derivative of cotangent is negative cosecant squared. And we also have derivatives of the inverse trig functions. Derivative of inverse sine is 1 over root 1 minus x squared. Derivative of inverse cosine is the same as the inverse sine, but with a negative. Derivative of inverse tangent, 1 over 1 plus x squared with no square root. Derivative of inverse cotangent is the same as the derivative of inverse tangent, but negative. Derivative of inverse cosecant, yes, I did go out of order there. Derivative of inverse cosecant, negative 1 over absolute value of x, root x squared minus 1, and derivative of inverse secant is the negative of the derivative of the inverse cosecant, also known as positive 1 over absolute value of x, root x squared minus 1. So these 22 derivative laws, there is a separate PDF on Canvas with these laws listed out across 4 pages. So that's definitely a good thing to look at, especially while you're doing, well, especially as we go through the examples we're going through. In a lecture, when I go over these, I usually put all of these laws on a sideboard and then do all the work on the front board referencing the sideboard. So to simulate that, you can open up the derivative laws PDF posted in week, I don't know what week this is, week 5, week 6, whatever week this week is. Open up that PDF and have that visible while we're doing these examples. So let's do a bunch of examples of just derivative computations. And here I'm going to use the fractional, actually I'm going to use the f and f prime notation here. So all of these examples, the directions will be find f prime of x. So let's do this one first, 4x squared. And let's do it in a good amount of detail, this one. How would we do the derivative of 4x squared? Well, you could use the definition. I would recommend not doing that unless you're told you have to. Well, how can we do this? Well, we have 4 times x squared. 4 times x squared. Well, the third rule said that we could pull the constant out front. So let's do that. Let's just leave the 4 there. If you leave the 4 there, then all you have to deal with is the x squared part. Well, we already dealt with the 4, so let's just get rid of the 4. And now we need the derivative of x squared. Well, the derivative of x squared, we would use rule 2, the power rule. X to the n with n equal to 2. If n equals 2, on power rule, the derivative is 2, x to the 2 minus 1. Well, 2 minus 1 is 1. And x to the 1 is just written as 2x. Or x to the 1 is just written as x. So 2 times that is 2x. So here, we have the derivative is 4 times 2x, which we can just write as 8x, which we should just write as 8x. So how did we do this? Well, we left the 4 alone using rule 3, and then we took the derivative of x squared using the power rule, and we got 2x. So we left the constant alone, derivative of x squared is 2x, and then we just combined the 4 and the 2. How about this one, 3x to the negative fifth? Example. I'm not going to write example that time. This time. These are all examples. F prime of x. Well, again, we have a 3 out front, so let's just carry the 3 down. One of the most important things in calculus, quite possibly the most important thing in calculus, is realizing when you have a constant out front and you can just carry it through. What do I mean by carry it through? Well, when I see this function up here, I don't even see that 3. Because I know the rules tell us that if we just write the 3 in each step, then we'll have taken care of everything we need to take care of regarding that 3. What we have to worry about now is the x to the negative fifth. Well, which of those 22 rules does x to the negative fifth fit into? Well, that's another power rule. Rule 2. Rule 2, we have x to the negative fifth, that's x to the n, with n equal to negative 5. Well, how do you take the derivative of x to the negative fifth? Well, you let n equal negative 5. Well, you don't let it equal, it is equal to it. The derivative of x to the n is n x to the n minus 1. Negative 5 minus 1. So we have negative 5 out front. X, negative 5 minus 1 is negative 6. So let's just rewrite that negative 5, x to the negative 6. Well, we can just simplify that a little. In general, I won't ask you to simplify, but I mean, when you have like a 4 times 2, you should simplify that. When you have a 3 times a negative 5, you should simplify that to that negative 15. When you have like some of the next examples we'll do, you don't necessarily have to simplify. So here, we pulled the 3 down, and then we dealt with the x's using a power rule. When you're doing these derivatives, it's also a good idea to sort of block off the x's and block off the things without x's in your mind. Let's do another. Find the derivative of this function. (7x minus 5x to the 4). Well, what do we have? We have 2 things added together. 2 things with x's added together. I mean, they're added with a negative sign, but they're still 2 things added together. So if we want this derivative, if we want the derivative, we should write that we're getting the derivative. If we want this derivative, rule 4, yes, rule 4 told us that if you want the derivative of something minus something else, well, then you need the derivative of the first thing, and then you subtract the derivative of the second thing. So let's do that. Let's do some side work on this 7x. How do we do the derivative of 7x? Well, the 7 just goes through by the constant rule. Great. Halfway there for this first half. So I guess we're a quarter of the way there. 7x. What is this x? Well, 7x is just 7x to the first power. X to the first, well, we can take that derivative using the power rule again, with n equal to 1. What do we get if we simplify that? So we get, let's just ignore the 7. We already took care of the 7, so I don't have to look at that anymore. Well, how do we take the derivative of this x to the first? Well, with a power rule. What does the power rule say? It says the derivative would be 1 times x to the 1 minus 1. Let's simplify that. 1 minus 1 is 0. 1x to the 0. Maybe when we multiply things by 1, we don't even write them. What's x to the 0? That's a 1, not a 7. Jeez. X to the 0 is 1. So the derivative of x, using the power rule, is 1. So the derivative of 7x is 7 times 1. Maybe I'm not going to write the times 1. Derivative of 7x is 7 times 1, which is just 7. And that example generalized, well, let's finish this and then generalize that. So derivative of 7x using a constant rule, rule 3, and a power rule, rule 2, the derivative of that is 7. Well, then we have to subtract the derivative of 5x to the 4th. Well, how can we do with 5x to the 4th? Well, that's just like the first 3 that we did. Derivative of 5x to the 4th is 5 times, use the power rule on x to the 4th, nx to the n minus 1, so 4x to the 4 minus 1. 4 minus 1 is 3, so we have 4x to the 3rd. 5 times 4 is 20. So the derivative here, 7, negative 20, x to the 3rd, using 2 power rules. Let's do this one. Equals cx, where c is a constant. Derivative of constant times x, well, this is what we talked about up here with the 7. Derivative of a constant is, or the derivative of a constant times x, well, pull the constant down. Derivative of x is just 1 by that argument up there, using a power rule. Because it would be 1x to the 0, which is 1 times 1, which is 1. And of course, that's just c, so I'm not even going to write an extra equal sign. I'll just say f prime of x, constant times x equals c. That's not the same as that constant multiple rule. The one that said the derivative of constant times a function is just the constant times the derivative of a function. This is a special case of that. How about this? F of x equals x cubed sine of x. Well, how do we take this derivative? Maybe I should have used the other notation for this, because now we have f's all over the place. Well, whatever, I can't stop it now. F prime of x equals, this will take a little bit of space, so I'm going to do side work down here. So the answer is going to be above that line. The side work will be below the line. What do we have here? Well, we have x cubed sine x. X cubed sine of x, in its most basic sense, is one function times another function. One function times another function, they form a product, so we will use the product rule, rule 5. Rule 5 said the derivative of f times g, so the derivative of f times g was f prime of g, or f prime times g, plus f g prime. So that's what we need to do here. Here we have one function, here we have another function, so the derivative will be done using a product rule. Well, for this, all we have to do is fill in these 4 pieces. 5 pieces if you include the addition sign. Well, let's start with the derivative of the first. The first is x cubed. The derivative of x cubed, using a power rule, is 3x squared. 3x to the 3 minus 1, and 3 minus 1 is 2. Well, okay, that takes care of this part. Now we need g. Well, g is just sine x. Okay, good. Halfway done. 2/5 of the way done. Positive sign. 3/5 of the way done. Now we just need f g prime. What's f? Well, f is x cubed. Too many f's. Too many f's. Down here, I'm not using that f up there. And I had a feeling there was a reason. in my notes, you might be able to see this, in my notes, I didn't use the F notation, F and G notation. So there was a reason for that. I should have paid attention to what I wrote. Where were we? We're doing a product rule. Well, we did first, derivative of the first times the second plus the first. Well, the first is just x squared. Sorry, x cubed. 4/5 of the way done. And then we need the derivative of the second. Derivative of sine, well, we use the, what was it? It was 11th in that list that I wrote on the board. It was the one over here. The derivative of sine is cosine. 5/5 of the way done. So right here, we used a product rule. Let's go through this one more time just by looking at this answer. Let's ignore all this stuff I wrote underneath it for now, or for this explanation. Because when you do a lot of these, you won't have to write out that side work. You'll be able to just do it from looking at this. So how do we do the derivative? Well, we have a product of two things. Derivative of the first, 3x squared, times the second, plus the first, x cubed, times the derivative of the second. And remember, both of those derivatives were found using those rules. So we have derivative of the first times the second, plus the first, times the derivative of the second. And when I'm doing product rule, I usually don't say F and G. I usually just say first and second. Just like with a quotient, I don't say F and G. I say top and bottom. Because F and G are too complicated, I think. Let's just call them what they are. The first function and the second function. Top function and the bottom function for a quotient. Speaking of quotients, is that my next example? Yes. Speaking of quotients, find the derivative of this function. Maybe I should put a negative sign on one. Nah, I'll leave positive. That's how I wrote it there. Let's find the derivative of this function. Now, right here, we have a quotient. Side work. We have a quotient. The derivative of a quotient is what? Bottom derivative top minus top derivative bottom over bottom squared. So bottom derivative top minus top derivative bottom over bottom squared. So let's do that. Bottom. What's the bottom function? What's the bottom function? The bottom function is tangent. So just write the bottom function. So that takes care of this part. Now we need derivative of the top. We need to multiply that, so let's use parentheses for multiplication. Derivative of the top. Well, the top, what do we have? We have x squared plus 2x plus 3. How do we do that derivative? Well, the derivative of x squared uses a power rule. 2x to the first, which is just 2x. Derivative of 2x, remember, the derivative of a constant times x is just the constant. Or you could go through the details with another power rule. Plus, remember, we have three things added together. We want the derivative here. We just do it one piece at a time. We keep adding them together. So the derivative of x squared, 2x. Derivative of 2x is 2. Plus the derivative of 3. What's 3? Well, 3 is just a constant. 3 doesn't have any x's. 3 is a constant. Derivative of a constant from rule 1 is 0. Yes, this is the first time we're seeing the derivative of a constant. Derivative of a constant is 0, so the derivative of x squared plus 2x plus 3 is 2x plus 2 plus 0. So 2x plus 2, and I'm not going to write plus 0. Well, okay, that took care of this part. So we have bottom derivative top minus top. So let's write that, minus top. There's minus top. Times derivative of the bottom. So what's the derivative of the bottom? Well, the bottom function is tangent. The bottom function is tangent. The derivative of tangent was given over here somewhere on that initial board. Derivative of tangent was secant squared. So just write that. So we have bottom, derivative top, minus top, derivative bottom, all over bottom squared. Bottom squared, just tangent squared of x. And when you're doing any of these, it's always a good idea after you're done writing to just check your work. Every time I do one, I check my work because it's very easy to write something wrong in these. Quotients, we have bottom, derivative of the top, which is 2x plus 2 equals 0, minus top, derivative bottom, secant squared, all over bottom squared. And you don't have to simplify that. And that'd be a real pain to simplify. Let's do another. Find the derivative of this function. Derivative of log of x with base 9. Well, this one would use the 6th, 7th, 8th, 9th rule. 10th rule. 10th rule that was listed. Derivative of a logarithm with a base other than e. Well, derivative of log x with base b was 1 over x log b, natural log b. So it's 1 over x, natural log of the base. In this case, the base is 9. Let's do another. F of x. Let's do this one. Let's change it to a different number than 9. Let's use a prime number. 7. I'm told that my 9s sometimes look like A's. I haven't figured out a way around that. I couldn't train myself to write A's like that. So who knows? Maybe in the future I'll figure out a way to make my 9s not look like A's. And I figured out how to make my 2s not look like Z's by crossing my Z's. But 9s and A's, haven't figured that one out in a convenient way yet. So let's change that to a 7 for this example. New example. Derivative of x log of x with base 7. Well, what do we have here? We have two things with x's multiplied together. So we're going to use a product rule. So we have this thing and then this thing. You could also use an underline, double underline to separate them like that. Derivative of x. Derivative of x. Well, what's the derivative of just x? Well, x is 1 times x. The derivative of a constant times x is the constant, so the derivative of 1 times x is 1. Because 1 is a perfectly reasonable constant. Good job. Where was I? So we want the derivative of this product. Derivative of the first is 1. Guess I'll write that. Times the second. So just leave the second without changing anything. Plus the first times the derivative of the second. Well, what's the derivative of the second? Well, the second is a logarithm function. I mean, it's the same as this up here, but with base 9. But you could suppose you don't have the answer right in front of your eyes. You could suppose you have to go back to the list of derivative rules. And it would tell you derivative of log of x with base 7 is 1 over x log 7, natural log 7. And then this one, I mean, that answer looks kind of messy, I think. So we can just simplify it a little. And the 1 times that looks kind of stupid. So I'll just write that as log of x with base 7 plus, and then the x's cancel, which is kind of nice there, plus 1 over log 7. Frequently in math, natural log is not actually said. It's usually just called log. But in that example, we had a product rule. Derivative of the first times the second plus the second times derivative of the first. I misspoke. Derivative of the first times the second plus the first times the derivative of the second. You could do that in the other order also, of course, because you can add in whatever order you want. How about the derivative of this function? Some of you might be saying this. Some of you might be saying that, trying to apply a power rule to e squared. E squared is not a power function. Incorrect. So this was gotten by pulling the constant down and then doing a power rule on that. Incorrect, because e squared is not a power function. What if you tried this? Rule 7 said the derivative of e to the x was e to the x. Derivative of e to the x is e to the x, so the derivative of e squared is e squared. Well, that is also incorrect. Derivative of e to the x is e to the x. E squared is not e to the x. 2 is not a variable. 2 is a number. So what is this function? Pi times e squared. Well, pi is a number. E is a number. So pi times e is just some random number. It's something in like the 20s or something. But it's a number. Rule 1 tells us how to take the derivative of a number. Derivative of a number, of a constant, is just 0. Let's do this example. Example. Find f prime of x. I don't really like that example. Yeah, okay, let's do this one without simplifying it. 4x squared minus 7x to the negative 2 log x. You could distribute that out. I'm not going to, because if we distribute that out, then we'd have to do 2 product rules. If we leave it like this, we'd have only 1 product rule. And I would prefer to do it once rather than twice. So right here we have something times something else. Both of them have x's. So we can use the product rule. Derivative of the first, well, we have a couple power rules with the constant rules here. So let's do that in one step. Derivative of 4x squared is 4 times 2x, which is 8x. Derivative of negative 7x to the negative 2, well, just like with this one, we pull the negative 2 out front. That gives us a 14 times x to the negative 2 minus 1, which is negative 3. And I should probably write a little smaller so this all fits on the board. So f prime of x equals what? 8x positive 14x to the negative 3. That's only a small part of our answer. We have a product, so the derivative is the derivative of the first times the second. So log x plus the first just rewrite the first one times the derivative of the second. Derivative of log x using rule 128 is just 1 over x. You could have also used rule 10 with b equal to e if you wanted to, but I separated the natural logarithm and natural exponential in those rules. So we have first, we don't have first. We have derivative of the first times the second plus the first times the derivative of the second. You don't have to simplify that, even though it looks like it, well, that would simplify a little nicely on that side. You don't have to simplify unless you are told to simplify. And there will actually be many examples where you're told not to simplify these. Because, well, maybe I'll explain in this next one. Find f prime of x. E to the x plus x over cosecant of x. Well, we have a quotient, so we're going to have to use our quotient rule. What does quotient rule say? Well, it tells us the answer is going to be some large quotient, so let's just write a large fraction bar at the start. Quotient rule says the derivative of a quotient is bottom times derivative of the top. What's the derivative of the top? Well, the top is what? E to the x plus x. So it's something plus something else. So you can do the derivative one piece at a time. Derivative of e to the x is itself plus derivative of x, well, that's a constant times x. Or it's a 1 times x. Derivative of 1 times x is 1. So we have bottom derivative of the top. Bottom derivative of the top. Itself plus 1. Minus top derivative of the bottom. Derivative of the bottom. I apologize, I'm changing this example slightly. I'm going to change that cosecant to a secant. So how does that change our answer so far? Well, it changes that to a secant. I'm changing that to a secant. I'll explain why in a moment. So we have bottom, derivative top, minus top, derivative of the bottom, derivative of secant. Secant x, tangent x. All over bottom squared. So we have bottom, derivative top, minus top, derivative bottom, over bottom squared. When grading questions like these, that is exactly how they are graded. You look for bottom, derivative top, minus top, derivative bottom, over bottom squared. This one actually does simplify because everything has a secant on it, but we won't simplify that. Now, how would this change if it were a cosecant on the bottom? Let's do that one. So, since I have a board here, it's easy for me to turn this one into a cosecant. Might not be as easy for you taking notes if you're taking notes. But how would that change? Well, bottom, derivative top, minus top, derivative bottom, over bottom squared. So let's change this also to a cosecant. So that would be changed, that would be changed. And this over here would be changed. How would this be changed? Well, the derivative of cosecant is negative cosecant cotangent. And this is a perfectly acceptable answer. I personally don't really like this answer. You would get full credit if this were your answer. But whenever I have an extra negative here, I usually just like to combine these two negatives into a positive and get rid of that negative. And this is why I wanted to change that first example. Because in that first example, I would have just written it as a plus, and that would have been quite confusing as a first example or a second example. But now it's the third example. We can check our answer here. Derivative here, bottom, derivative top, minus, that's not a minus, but let's keep that in mind. Bottom, derivative top, minus top, derivative of the bottom is that negative cosecant cotangent, all over bottom squared. My magic eraser is quite squeaky today. I don't know if that's showing up in the recording. Probably is. That microphone is pretty strong. It's right in front of me. Let's do this one. Derivative of 7 to the x cosine x. Well, again, we have two things multiplied together, so we're going to need a product rule. Derivative of 7 to the x. How do we do the derivative of 7 to the x? Well, that's 7 to the x. That is a number to the x. Rule 9. Yes, 9 will apply to this with b equal to 7. The derivative of b to the x is b to the x log b. So the derivative of 7 to the x is 7 to the x log 7. And that's just part of our answer. But let's write down this part of our answer. Because if we write down enough parts of our answer, then we'll get the right answer. Where were we? we have two things multiplied together. Derivative of the first is that. Then just write the second one. Let's write it correctly. Don't want to lose credit for miswriting a couple letters. So we have derivative of the first times the second plus the first times the derivative of the second. Derivative of cosine is negative sine. Derivative of cosine is negative sine. And you could leave your answer like that. But again, like that last example, I'm going to just pull the negative out front. I mean, you don't have to simplify these, but there are some simplifications that you kind of get used to doing, and that's one of them, just putting a negative out front. So we have derivative of the first times the second plus the first times the derivative of the second with that negative sign. Let's do this one. We haven't done any inverse trade yet, so let's do some inverse trade. Those are fun. Yeah, let's do e to the x, I guess. Let's do sine inverse of x. Sine inverse of x, that is not sine x to the negative 1. That's different. This is the inverse function. Well, again, we have a product rule. Two things multiplied together. So the derivative is done by doing the derivative of the first times the second plus the first times the derivative of the second. Derivative of e to the x is itself times the second plus the first times the derivative of the second. What's the derivative of the second? Well, the derivative of sine inverse x from rule, the sixth to last rule, so that would make it rule 17, is what? 1 over 1 minus x squared, all under a square root. And you could rewrite this as e to the x over root 1 minus x squared. I'm not going to. So here, let's check our work. We have the derivative of e to the x times the second plus e to the x times the derivative of the second. Let's do this one. Derivative of 4 inverse tangent of x. Well, there's a 4 out front. Taken care of. Now we have an inverse tangent of x to deal with. Well, the derivative of inverse tangent of x is 1 over 1 plus x squared. So there's an answer. I don't really like how that looks. So I will just rewrite that as one fraction. I guess that's slightly inconsistent with what I said about the last example and not writing that second fraction as e to the x over root 1 minus x squared. But that's okay. We're allowed to be inconsistent a little sometimes. If it makes the answer look that much better, then I'll simplify it. But of course, this up here is an acceptable answer. Are we allowed to be inconsistent? I don't know. I don't think I've taken off on any tests for inconsistency. Let's do another. This one probably won't fit on the board, so let's change it a little. This one. Secant x plus 4e all over x to the negative third cotangent of x. Well, that's a lot of math symbols, but what is it? It is a quotient. So to do its derivative, we will use the quotient rule. So we just follow the quotient rule. Quotient rule says derivative quotient is bottom. So just write the bottom. Derivative of the top. I'm going to use square brackets this time. I don't know, maybe that'll help the organization. In these, I find lined paper very difficult to use for computing derivatives. I think it's very complicated to look at lined paper for these. Where were we? Bottom, derivative of the top. Well, derivative of the top, we have two things added together, so we'll do them one piece at a time. Derivative of secant is secant tangent. Secant x, tangent x. Derivative of 4e. Well, 4 is a constant. E is a constant. So derivative of 4e is 0. So I could write a plus 0 and then end the square bracket, but instead I'm just going to write it like that. Maybe I'll put them in parentheses. I don't know, whatever. Put them in parentheses to make checking my answer a little easier. So we have bottom derivative of the top minus top. And then we need derivative of the bottom, which we're going to write in that large parenthesis. How do we do the derivative of the bottom? How much space do I have? Jeez. I hope this all shows up. If not, you'll just have to listen to what I say. I think this entire board is showing on camera. I don't know, can you see the thermostat in here? There's a thermostat about 1 marker's length from the board, in case you can't see what I'm referring to. Where were we? Bottom derivative of top minus top derivative of the bottom. Well, the derivative of the bottom, we have a product. So we'll use the product rule. Derivative of x to the negative third, negative 3x to the negative 4. Leave cotangent alone. Plus the first times the derivative of the second. Derivative of cotangent is negative cosecant squared. So negative cosecant squared, that's not what I wrote. Negative cosecant squared, I'm going to take care of that negative by just turning that into a negative. So we have derivative of x to the negative third, negative 3x to the negative 4, cotangent x minus, negative 3x to the negative 4, cotangent x plus x to the negative third times negative cosecant squared of x. From rule, whatever the last rule was for cotangent. And this would be a lousy spot to end our answer because we did all of that work and would not get full credit because we didn't divide it by the bottom squared. And I'm just going to write that like this. You could write it x to the negative 6 cotangent squared x. I'll just write it like that. So let's check our work. So we have bottom, derivative of the top, plus 0, minus top, derivative of the bottom, all over bottom squared. In case you can't see it, maybe I'll go over to this camera and let's see if this screws everything up. There, now you can probably see the thermostat and the hallway. But you can also see the rest of the answer, definitely. I don't know if I mentioned this before. This whiteboard and the chalkboard are in my living room. Thermostat is set where? Let's see, 50? Yes, 50. It got below freezing the other night up here. And we don't want pipes freezing because that's a real pain. So I have it set at 50 in case pipes freeze, or in case it gets cold enough that pipes freeze. Let's do another. Oh, I did one just like this, didn't I? Yeah, I did the same thing with inverse sines. I'm not going to do this one. Let's do this one. 1 plus 4x squared. 4x squared has shown up like 3 times. Let's just do 4x. Plus 4x minus 7x cubed times cosine x minus cosecant x. And let's hope our answer fits on the board. So where are we? We have a product. You don't have to, you could multiply this out. If you did, you'd have, what, like 4 different product rules to deal with. So I'm just going to leave it as it's written. Derivative of the product, derivative of the first. How did I get that? Well, derivative of 1 is 0 because 1's a constant. Derivative of 4x is 4 by the power rule and the constant rule. Derivative of 7x cubed is 21x squared because 3 times 7 is 21, and then there's a negative sign. So we have derivative of the first times the second plus the first times the derivative of the second. What's the derivative of the second? A lot of negative signs here. Derivative of cosine is negative sine. Derivative of cosecant. Before I said derivative of cosecant, I should have said negative sign. There's that negative sign. Derivative of cosecant is negative cosecant cotangent. So we have negative sine minus a negative cosecant cotangent. And I'll just write that minus a negative as a positive sign. Let's do this one. X to the 7/5. Well, 7/5 is a number. So the derivative of x to the n, remember, is n x to the n minus 1. So if n equals 7/5, well, pull the 7/5 out front, and then you get x to the 7/5 minus 1. That's written very poorly. But we just have another power rule. It's not a whole number as the exponent, it's a fraction, but we can still use the power rule on that. So we have 7/5 x to the 7/5 minus 1. What's 7/5 minus 1? Well, 7/5 minus 1 is 7/5 minus 5/5. 2/5. So we have 7/5 x to the 2/5. So let's do another. Four x to the 2/3. Now let's make it more interesting. Minus, I think I already did a sine inverse. Let's make it really annoying. Minus 3 secant inverse of x. Nah, really, that's mildly annoying. So let's do this derivative. So we have 4. Well, let's just write the 4 so we don't have to think about it anymore. X to the 2/3. Well, again, we have the power rule. 2/3 x to the 2/3 minus 1. What's 2/3 minus 1? Well, that's 2/3 minus 3/3. 2 and negative 3 make a negative 1. So 2/3 minus 3/3 is negative 1/3. So we have 4 times 2/3 x to the negative 1/3 for that part. And then for the other part, well, we have a negative 3, and then we need the derivative of the inverse secant of x. Well, what's that? It's 1 positive 1 over absolute value x root x squared minus 1. And you could leave the answer like this. I'm not going to. 4 times 2/3 gives us 8/3. And then I'll just write that as 3 absolute value x squared minus 1 under square root. Let's do one more. I think I've covered every rule. I mean, I guess I didn't do an inverse cosecant, but I mean, it's the same as inverse secant except with another negative sign on it. I don't think I did an inverse cotangent either, but again, that's the same as the... Yeah, I think I did all the trig functions. The inverse cotangent is the same as the inverse tangent with another negative sign on it. Let's do this example. We'll see this function again. Derivative of x log x. Well, it's a product rule. Derivative of x is 1. So we have 1 times the second plus x times the derivative of the second. So we have, maybe I'll write the 1 out here. 1 log x plus x times 1 over x. So that's just log x plus 1. It simplifies nicely. So we have derivative of the first times the second plus the first times derivative of the second. Now, I have a couple useful remarks. Well, useful in the sense that they will make certain things we do for the rest of the, or in the future, a little easier to jump straight into. So, remark. I'm just going to say these are quite useful to get used to. There's a good sentence. These are quite useful to get used to. Remember, we had multiple notations for the derivative. One of the notations was written like this: d over dx of some function. So derivative, this is just read, the derivative of 1 over x with respect to x is negative 1 over x squared. And the derivative of root x with respect to x is 1 over 2 root x. Now, these are useful. Why am I saying these are useful to get used to? Well, if you actually were to do the derivative of 1 over x, how would you do the derivative of 1 over x? Well, 1 over x is x to the negative 1. So, derivative of that would be a power rule, negative 1, x to the negative 2. So you could write it like this. You could also write it like this. There will be times where we deal with these and we actually want them to be written as fractions. So you could go through the power rule argument like this, or you could get used to derivative of 1 over x being negative 1 over x squared written like that. Of course, they're the same. But it's useful. It will be useful many times to jump straight from 1 over x to negative 1 over x squared without having to go through that power rule argument. And similarly over here, for root x, well, how would you do the derivative of root x? Well, root x is x to the half. So the derivative of x to the half would be a half x to the half minus 1, which is negative a half. And you could write your answer like that. There will be things we do in this class where having it written like that is not very useful. But if you simplify that, remember x to the negative 1/2 is just 1 over root x. So you could simplify that as just this fraction like that. So I'm going to make this remark now, because we'll see later in the class there will be a bunch of times where these two functions come up and we need their derivatives, and we need to actually do things with them beyond just computing the derivative. So keep these in mind. Now, what can we do with the derivative? Well, we can do a bunch of things with the derivative. one thing we can do is find equations for tangent lines. So let's do a couple examples. Find an equation for the line tangent to this function equals what? 3x squared cosine x at x equals pi. So we need a tangent line. So we need an equation for a line. Well, we're told equation for a line. So we need a point and a slope. If you take Calc 3, which some of you probably will be taking Calc 3, Calc 1 and Calc 2 are on the xy plane. Calc 3 adds a third dimension to that toward the beginning of the course. And lines in Calc 3 are much more complicated than lines in Calc 1 and lines in algebra. But if you always keep in mind that all you need is a point and a Calc 3 slope, it will make finding an equation for a line much, much easier. So, for those of you who will be taking Calc 3, it will probably not be explained to you in Calc 3 that you need a point and a Calc 3 slope. But keep that in mind, and it'll make a lot of your life easier in Calc 3. Point and a slope. Point and a slope. Well, what's our point? Well, the x value is pi. What's the y value? I don't know. Let's find the y value. The y value is 3 pi squared cosine pi. What's cosine of pi? I don't know. All I know is this circle tells us. Pi is over there. Cosine is the x value. So cosine of pi is -1. 3 pi squared times -1 is -3 pi squared. Well, that's wonderful. That gives us most of our, well, half of our answer. Now we need the slope. Well, remember, the derivative gives us the slope. We want the derivative evaluated at pi. Well, first we need the derivative. So let's find the derivative. I'm going to do the derivative work over here. So what's the derivative? Well, we have 3x squared times cosine x. You could just write the 3 and then deal with x squared cosine x. I'm going to have the 3 be a part of the first term. In other words, derivative of 3x squared, well, I guess that's not in other words. As a result of having the 3 being part of the x squared, the derivative of 3x squared is 6x. Leave the second alone, plus the first times the derivative of the second. Derivative of cosine is sine. Sorry, derivative of cosine is negative sine. So we have the derivative of this function, 6x cosine x plus 3x squared times negative sine x, and the plus and the minus make that a negative. So what's f prime at pi? F prime at pi equals, I'm going to write the answer here, I'm going to do the side work over here. F prime at pi equals 6 pi cosine of pi minus 3 pi squared sine of pi, and I shouldn't have erased that circle because I need it again. Pi is over here. Cosine of pi is -1. Sine of pi is 0. So we get that f prime of pi is -6 pi plus 0, so just -6 pi. Well, that was a lot of work we did to not get full credit, to get full credit, we would need to write this as a line equation. So y minus the y value equals slope times x minus the x value. You don't have to simplify that, even though that does simplify a little. What would it simplify to? Y equals negative 6 pi x plus 3 pi squared. But before, when we were asking for tangent lines, you needed to go through the definition of the derivative. But here, we just used our algebraic derivative laws. Another type of question we could be asked, at which values does this function have a horizontal tangent? At which values does it have a horizontal tangent? Well, what does a horizontal tangent look like? It's always nice to have a visual in calculus for what you're actually trying to find. A horizontal tangent looks like this, or it looks like this. In other words, it's where the derivative equals 0. So it's the x value at which the derivative is 0, and similarly for that one. So all we need to do to find horizontal tangents is find where the derivative is 0. So let's do that. To find where the derivative is 0, we would first need the derivative. So what's the derivative here? Well, we have a bunch of power rules. Derivative of x cubed, 3x squared. Derivative of negative 7x, well, the negative 7 carries through. Derivative of, so it would be negative 7 times derivative of x squared, which is 2x to the first. So negative 7 and 2 make 14 with a negative sign. Negative 4, that doesn't factor, that's great. Well, let's see. Well, it might factor. Derivative of 8x, 8 is a constant. So the derivative of 8x is 8 plus 3, or plus the derivative of 3. The derivative of 3 is 0. And we want to set this equal to 0 to find the horizontal tangents. This looks like it will factor. So what do we want? We want, yeah, this is going to factor. I knew I wouldn't have chosen an example where it didn't factor. So we need numbers. This is a prime, which makes it much easier. So what would give us a 14? We would need a negative 12 and a negative 2. So that'll make 14, that'll make 8. So we want to set those equal to 0. I'm just going to finish it over here. Set the first one equal to 0, you get x equals 2/3. Set the second one equal to 0, you get x equals 4. Let's check my work. Yes, that is right. If you, in this class at least, if you go through one of these and you have to deal with something like this, if it's a prime out front, it probably will factor in an example I give you. If it's like an 8 out front, I highly doubt I would ever have you do one with an 8 out front. Or some other annoying number. If it's a prime, I might ask for that, because the fact that it's prime restricts your choices right at the beginning. Let's make one final remark. So we've taken first derivative so far. We can take derivatives after that, meaning if you have a function, you can take its second derivative, or you can take its third derivative, and so on. And we call those higher order derivatives. And the notation we'll use for the second derivative looks like this. F prime prime of x, or F double prime of x. So we have two of those apostrophe-like things up there. Or y double prime. Or d2x over dx squared. With second derivatives and the higher order derivatives, third and fourth and so on, I'll pretty much stay with these two notations. Well, pretty much. I'll definitely stay with these notations because this gets a little messy. But let's look at an example. Let's find the second derivative. Example. Find f prime prime of x, or f double prime of x, for this function. Equals what? 7x to the fifth plus 3 sine of x plus 4. Let's make it a negative sign. Why not? I feel like I haven't done that many negative signs today, or maybe I feel like I've done a lot of negative signs. I don't know. I feel like one of those ways. So let's find the second derivative. Well, to find the second derivative, we first need the first derivative. So let's find the first derivative. Well, here we have a power rule. 7 times 5 is 35. X to the fourth. Derivative of sine is cosine. Derivative of negative 4x, just negative 4. Well, that's not the answer. It tells us to find the second derivative. So we need the derivative of this. 35 times 4 is 70 times 2 is 140. X to the third. Derivative of cosine is negative sine. Derivative of negative 4 is 0. And notice in that, for that trig one, the 3 just kept carrying through. And we don't necessarily have to stop ourselves at the second derivative. So we could take third derivatives, we can take fourth derivatives, and so on. Keep going. So, new example, find the third, fourth, fifth, sixth, find a bunch more of these next derivatives. Find some higher order derivatives. In other words, keep going. So the third derivative, well, we do the same thing, the derivative of the second derivative. 140 times 3 is what? 420, because 14 and 3 make 42. X squared. Derivative of sine is cosine. So derivative of negative 3 sine is negative 3 cosine. And so on. Let's find the fourth derivative. I'm going to go up here. In your notes, if you're taking notes, you might want to go down for the next couple. I'm going to go up because I don't want to write on the walls. Fourth derivative, I'm going to write it like that. That's a relatively standard notation. Instead of writing prime, 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 write an IV in parentheses for fourth derivative of x. Well, what's the fourth derivative? 420 times 2 is 840 times x to the first. Derivative of cosine is negative sine. So the negative and the negative make a positive. Let's do the fifth derivative. The fifth derivative, well, the derivative of 840 times x is just 840. Derivative of sine is cosine. Let's find the sixth derivative. Derivative of 840 is 0. Derivative of cosine is negative sine. And so on. So I'll say dot, dot, dot. So you can take derivatives of derivatives. Now, one thing I'd like you to observe with this, the original function was, the trig term in that was 3 sine of x. And notice that showed up again in the fourth derivative. So you started with 3 sine of x, and then the fourth derivative brought you back to 3 sine of x. And in the first derivative you had 3 cosine x, and in the fifth derivative you also had 3 cosine x. In the third derivative you had negative 3 sine x, and the sixth derivative you had negative 3 sine x. So you can see that these trig function derivatives kind of cycle around. And that's a very important thing in certain branches of higher level math. But it is something I mean, we won't really use that in Calc 1 very much, but it is a good observation to make. So definitely be sure you understand how we did all of these derivative examples, because by the end of the semester, well, really by next week, these derivative computations do need to be kind of not automatic, but not something that causes you too much delay on, say, a final exam. Because next week, these derivative computations are going to get much more complicated. And having a solid foundation will help make next week go more smoothly. So definitely try all of the examples that I put on the worksheet. The worksheet is going to be a bunch of textbook problems, because the textbook problems are fine with derivatives. So definitely try to work through those. They're very important.